Hello, and here we're going to continue chapter 2. Would you believe I forgot what chapter 2 is all called? Approaches to problem solving. There we go. We're in unit 2B, extending unit analysis. So where we left off in 2A, we're going to pick it up and do some more unit analysis. Here we go. So there's two different ways of measuring things, and it's all the US's fault. The US has their customary system, and it has its roots dating back thousands of years, actually before US was the US, and its units became standardized in weird ways. So the length of a modern yard, right, which we all know is 3 feet, 36 inches, it was actually defined by the English King Henry I, who decreed it to be the distance from the tip of his nose to the tip of his thumb on his outstretched hand. Okay, now how am I supposed to measure that today? He's a little decayed. The table in your text summarizes all the official U.S. customary system. I think it's table 2B.1. It shows the standard units for length, weight, and volume. We still need a movement. There was one in the 70s. Try to get the U.S. to let go of this. But we just can't let the English go for some reason. Let's look at an example. The length of the Kentucky Derby horse race is 10 furlongs. How long is the race in miles? Well, in that table of U.S. customary measurements, you'll find that 1 furlong is 1/8 of a mile. Well, 1/8 of a mile is the same as 0.125 of a mile if we switch our fraction into decimal. And we could write the conversion factor in two other equivalent forms, right? We have 1 furlong equals 0.125 miles. Remember, just like we did with the feet and the inches, we can divide it by either side and it'll make a 1. So we could use this as our conversion factor. So we'll take 10 furlongs times 0.125 miles divided by 1 furlong. Furlongs cancel out. And we end up with 10 times 0.125 is 1.25 miles. Remember, we're always going to finish with an explain, write it as a sentence. Kentucky Derby is a race of 1.25 miles. All right, let's talk about food. You're planning to make a pesto and need to buy basil. At the grocery store, you can buy small containers of basil priced at $2.99 for each 2/3 ounce container. But at the farmer's market, you could buy basil in bunches for $12 per pound. Which is the better deal? If you've only got $3, you go for the one in the store, but, that's not what this class is about. To compare the prices, we need them both in the same units. We're going to convert the smaller one at the grocery store into a price per pound so that we can compare with common units. The container price is $2.99 per 2/3 ounce. So we'll write that as a fraction. $2.99 per or divided by 2/3 of an ounce. But we want to convert ounces into pounds, and there are 16 ounces in 1 pound, and so our conversion factor, we'll put the ounces in the numerator so that they cancel from the denominator. Why is ounces abbreviated with OZ when there's no Z in there? I still don't know. But I happen to know the pound is LB because of libre, scales. Not livre. I think it's libra. The scale, yeah, libra, it's the scales. It was an English word as well, the pound. Scales indicating we're weighing. So we can, let's see if I don't think they actually do cancel those out. Our units cancel out and we multiply $2.99 times 16 divided by 2/3. And if you're using a calculator, just throw a little parenthesis around that 2/3 to make sure you get the answer, 71.76. Our units in the numerator are dollars. Our units in the denominator are pounds. So that's dollars per pound. The small containers are priced at almost $72 per pound. That's like 6 times as much as the farmer's market price. Buy local. But there is a better way. A way that a lot of Americans are not very familiar with. But for us down here towards the border, more people are actually familiar with it. The International Metric System was invented in France late in the 18th century. Ben Franklin actually helped do this to them, and the U.S. almost adopted it before France. But the Founding Fathers said, nah. The reason France wanted to use it replace those customary units, right? King Henry was dead. We had no idea how long it was from the tip of his nose to his outstretched thumb. They want to change them to just a few basic units. And also use a base 10 system, so we just have to slide that decimal. The basic units of length, mass, time, and volume in the metric system are meters, abbreviated M. That's why I use an MI for miles. The kilogram, kg. Actually, it should be a gram. That is, kilo is not the standard. It's actually a gram, but very few things weigh less than a kilogram in the general scheme of things. So I can see why they might say the kilogram is the basic. Second for time, but that as only because we have nanoseconds that we can measure computing in now. Hours, days, years, those are all very common as well. There's no kiloseconds or anything like that that I'll be asking you to do, I don't think. And the liter for volume, abbreviated with an L. And you can see in this table, which is also in your book, this is 2B.2 table. And it'll show you the different ways of converting the abbreviations. So if you have a deciliter, you would write DL. If you have a centimeter, CM. If you have a milligram, mg. If you have a microgram and you're in science, you'll use mu grams. But if you're in the medical field, you'll probably call it mcg, micrograms. All right, so those two have the same meaning. And you can see here we have our fancy scientific notation, but right next to it, it's a 1 followed by this many zeros. And this negative tells me it's in the denominator. So 10 to the negative 3 is a 1 followed by 3 zeros. The negative tells me it's in the denominator. Over here, 10 to the 6, that's a 1 followed by 6 zeros. Because the 6 is positive, it's in the numerator, or it's just a standard 1 million. All right, so the negative tells us it's in the fraction. The number in the exponent tells us how many zeros to add behind the 1. Let's convert 2,759 centimeters to meters. First of all, centimeters are smaller than meters. So when we convert, we should have an answer that is smaller, right? We should have fewer meters than centimeters. Now our table, the one we just looked at, table 2b.2, shows that centi means 2 to the negative 2. So 1 centimeter is 2 to the negative 2 meters. Or it's a 1 followed by 2 zeros in the denominator. 1 meter equals 100 centimeters. There are 1/100th of a meter is 1 centimeter. And if we multiply both sides, we'll get 1 meter equals 100 centimeters. There we go. Therefore, 2,759 centimeters is the same as, and I don't believe this one actually takes the time to cancel it out, and is 27.59 meters. Centi is 100, so we just divide by 100, move our decimal place twice, and that's a lot easier than, say, converting yards to inches or inches to yards, right? There's weirdness going on. It's not just moving a decimal point. The marathon running race is about 26.2 miles. About how far is it in kilometers? We have a table. It's table 2b.3. I don't know why it's not labeled correctly. 2b.3 shows that 1 mile is equal to 1.6093 kilometers. We use the conversion in the form with miles in the denominator, right? The race is 26.2 miles. I need to cancel out miles, so miles will go in my denominator. And I'll multiply 26.2 times 1.6093. I'm doing this on my calculator for sure, right? And it should be 42.2 kilometers. Whoop, there we go. Excellent. Let's talk about temperature units. We have the Fahrenheit scale that we frequently use, where water freezes at 32 and boils at 212 degrees. The rest of the world, literally everyone but the United States, uses the Celsius scale, which places the freezing point of water at 0 degrees Celsius and the boiling point at 100 degrees Celsius. Totally makes sense, right? 0 to 100, it's like a lot like percentages. In science, however, there's a third scale, and it's the Kelvin scale, which is the same as the Celsius scale, except for its 0 point, which corresponds to negative 273 degrees Celsius. A temperature of 0 kelvins is known as absolute zero. It's the coldest possible temperature that mankind has found to be able to be in existence. We don't use the degree symbol on Kelvin scale. It's not degrees Kelvin, it's just Kelvin. All right, and here we see a nice little graphic showing how Fahrenheit, Celsius, and Kelvin register the temperatures. A lot of times you'll actually see Fahrenheit and Celsius on the same scale. Not on the same scale, on the same thermometer, two different sides, and you can look at both numbers at the same time. All right, the conversions from Celsius to Fahrenheit, Fahrenheit to Celsius, and in between Celsius and Kelvin are given in words and in formulas. I'm going to focus you in on this one and this one. If you have a Fahrenheit temperature, subtract 32, divide by 1.8. If you want it quick and dirty, I'm going to call this QD, it's quick and dirty. You take the Fahrenheit minus 30 divided by 2, and that's the approximate Celsius temperature. Like, if somebody tells you, yeah, it's about this, same thing here. We take 2 times the Celsius and add 30. It's a really good approximation, a quick and dirty approximation, but not an exact math approximation. We're going to use this formula and our formula to convert Kelvin from Celsius as well. Okay, the average human body temperature is 98.6 degrees Fahrenheit. What is it in Celsius and Kelvin? Convert from Fahrenheit to Celsius by subtracting 32 and then dividing by 1.8, right? Our Celsius is equal to F minus 32 over 1.8. So we put in 98.6, subtract 32, divide that answer of 66.6 by 1.8, and we'll get 37 degrees as the average human temperature. We find the Kelvin temperature by just adding 273.15 to the Celsius temperature to get normal human body to average, not normal, nobody's normal, average human body temperature of 98.6 degrees Fahrenheit, 37 degrees Celsius, or 310.15 Kelvin. But wait, there's more. I know this one's getting a little long. Some of them will be like that. Energy is what makes matter move or heat up. The international metric unit is the joule. Energy is different than power. Power is a rate, right? And anything that is a rate is a fraction at which energy is used. The international metric unit is the watt. So 1 watt is equal to 1 joule per second. A kilowatt hour is a unit of energy. You might find this on your electric bill. 1 kilowatt hour is 3.6 million joules. All right. My dogs are about to go off because the FedEx guy just drove up across the street. Be ready. A utility company charges 15 cents, example here, operating cost of just a light bulb. A utility company charges 15 cents per kilowatt hour of electricity. How much does it cost to keep a 100 watt light bulb on for a whole week? How much will you save in a year if you replace the bulb with an LED bulb that provides the same amount of light for only 25 watts of power? Okay, so we have a 100 watt light bulb, but we're charged in terms of kilowatt hours. So we need to change our watts into kilowatts, and 1 kilowatt is equal to 1,000 watts. So we'll multiply appropriately by the fraction. But we want to multiply that by a whole week, but a week is 7 days, and 7 days, 1 day is 24 hours, and so we have our big long string of multiplications. Oh, redundancy. I'll do 100 divided by 1,000. I'll hit enter, times 7 times 24, and I'll get 16.8 kilowatt hours. All right, so to have the light bulb, a 100-watt light bulb on for 1 week, it'll use 16.8 kilowatt hours. Now, I happen to know that each kilowatt hour is 15 cents. Right? So 15 cents per kilowatt hour. Notice. These are cents. 252 cents, 16.8 times 15. And with the kilowatt hours canceled out, that'll be $2.52. Now that's not too bad, right? I leave a light bulb on for a whole week. It cost me $2.50. No big deal. But check this out. The electricity for the light bulb costs $2.52 per week. But if you replace the 100-watt bulb with a 25-watt LED, you'll use a quarter as much energy, which means it'll cost a quarter of the cost. It'll only cost 63 cents. All I did, divide by 4, a quarter, right? Multiply by a fourth, divide by 4. When 63 cents, that's not bad at all. I'd rather pay 63 cents for a light bulb to be left on my vacation, and I'll save $1.89 per week. Over the course of the year, just by changing your 100-watt light bulbs to an LED bulb that provides the same light for 25 watts, you'll save $98 a year. I think I have like 8 light bulbs in the room I'm in right now. That can add up after a while. Who knew? I know, you probably did. Good job. Units of density and concentration. Density describes compactness or crowding. Material density is given in units of mass per unit volume, so grams per cubic centimeter. Population density is number of people per square mile, usually. Information density is given in units of mass per unit volume, so like gigabytes per square inch. Concentration, on the other hand, describes the amount of one substance mixed in with another. Concentration of an air pollutant is often measured by parts per million, whereas blood alcohol content is the number of grams of alcohol per 100 milliliters of blood. Right? So what's the concentration? Not the density, but the concentration. Let's look at our last example. A kid goes into the doctor and has an ear infection. They weigh 15 kilograms, and a physician orders treatment with amoxicillin at a dosage based on 30 milligrams per kilogram of body weight per day. You may have heard the doctor say this to the nurse or to the whoever happens to be taking their notes, a dosage. 30 milligrams per kilogram of body weight, divided into doses every 12 hours. All right, so we're going to look at how much amoxicillin should the child be taking every 12 hours, and then we're going to look at it in suspension form, right? If it's concentrated, like an IV drip. Okay, so to start with, how much amoxicillin should the child be prescribed every 12 hours? Now keep in mind, the dosage is 30 milligrams per kilogram of body weight per day, but it's going to be given in 2 doses every 12 hours. So 30 per day, that tells me it's 15 per dose, right? 15 milligrams per kilogram of body weight per dose. Therefore, a child weighing 15 kilograms, the dosage should be for 12 hours for 1 dose, 15 milligrams per kilogram, multiplied by the 15 kilogram patient. Kilograms cancel out, we'll get 225 milligrams. Now, if the medicine is to be taken in a liquid suspension with concentration at 25 milligrams per milliliter, how much should the child take every 12 hours? We know that they need a total of 225 milligrams every 12 hours. But how much liquid should we put that in? Right? 25 milligrams per milliliter. There's a couple of different ways that we should do it. I'm going to show you the hardcore math way first. It's not hard. It's just hardcore math. Let's check it out. All right, 225 milligrams divided into 25 milligrams per milliliter. Well, instead of dividing by this fraction, I need to switch this over because my units are different. So I'm going to change it to multiplication. where I have milligrams in the denominator so they can cancel out. And I end up with 225 times 1 over 25. That's 225 divided by 25, which is 9 milliliters. What this is really asking is how many times? Right, there's 25 milligrams, per 1 milliliter. So some of you might think of this as a ratio instead. And you could cross multiply and divide, and you see that you're doing the exact same math. So if you understand ratios of this form, unit conversions should come fairly easy to you. My goodness, it seems like I stuttered a lot on that one, but I swear the math's right. Let me know if you have any questions on the homework. Thanks for listening.